SN2 mechanism, nucleophilic substitution by molecular reaction, is said to be known as SN2 mechanism. In this mechanism, as I have told you in my previous lecture, that in this mechanism, both reactants, both reactant, both, one is organic compound, that is haloalkane usually, and other one is a nucleophile. Both reactant affect the speed of the chemical reaction. So two species can change, can alter the speed of reaction. That's why this is called SN2 mechanism, or SN2, nucleophilic substitution by molecular reactions mechanism. Mostly, as I told you, primary haloalkanes follow this sort of mechanism. Some secondary haloalkane may follow this one. Yes, it is true. And the next thing, as 2 is written over here, so this is one step. This is single step mechanism, only one step mechanism in which attacking or incoming nucleophile and the departure of the leaving group are happening simultaneously. There is attack of nucleophile and departure of the old nucleophile or leaving group. They are going to be in a systematic simultaneous process. As nucleophile approaches to the partial positive charge carbon atom, partially positive charge carbon atom is under attack basically. And as the nucleophile approaches that carbon atom, at the same time, because of the repulsion, old nucleophile, that is also said to be leaving group, start its journey to departure, to move away from that partial positive carbon. As a result, this CX bond, this C halogen bond, lengthen, or it becomes weakened as well, and ultimately a crucial stage is going to be over here, and it's breakdown. And during this whole process, this stage, this whole process, this whole story, this history is said to be transition state. At this stage, leaving group is near to leave, and formation of the new bond is almost complete. There are basically two immature bonds. One is that is being formed, other one bond that is being broken. None of the new bond has been completely made, and the old bond is not completely broken. To describe this state, theoretically, bonds are being formed, and broken are shown by the dotted lines. Ultimately, leaving group leaves the substrate permanently, and the new, that is called attacking or incoming nucleophile, becomes the part of substrate. Let's see over here in this picture. For example, this is the primary haloalkane. Its name is bromoethane. And here is the polar bond. This carbon is partial positive carbon. This Br is partial negative atom. And this is the new incoming attacking nucleophile. This incoming attacking nucleophile is going to attack from the backside of this old nucleophile. It is said to be old nucleophile. This is a representation or shortcut notation of nucleophile, old nucleophile. It is also said to be leaving group. It is also said to be leaving group. So this OH cannot attack from this side because of the repulsion of the electron of this old nucleophile or leaving group. So there is only one chance to attack, to approach this carbon, that is exactly from behind, from the opposite side of this old or this leaving group. So this OH is going to attack or going to approach this carbon from the opposite side of the Br. So this OH bond is going to attack over here. This is the curly arrow. And at the same time, this CBr bond is broken. And we are having, this is a symbol of transition state. This is the transition state. And moreover, noticeably, you can see, and you will write it over here as a negative charge. So this is called transition state. This is not known as intermediate. Why this is called transition state? Why this is not called intermediate? Because it is very short-lived product. It is short-lived species, very short-lived. It is just showing the transition state for the formation of, the final compound, and it's going to be formed just immediately before the formation of the final compound. And once again, you can see that these two bonds are shown by the dotted line. Why I shown it by the dotted line? Because this bond that is being formed and this bond that is being broken, none of the bond is completely broken or formed. So the next thing is it is having negative charge. Always you will put negative charge on transition state. You will mark bracket like the bracket in dot and cross formula of ionic compound, and you will mark negative charge on normally, usually, traditionally on the right hand side of this bracket, topmost right hand side. So this OH negative ion and this molecule that is called substrate mean basic original organic molecule. Substrate is a general name of any organic molecule that is under construction, that is under attack, and so on. So they are going to meet together. They are going to be added. Up till now, there is the addition reaction. So this is having negative charge, this is having OH group, Br, and so on. Finally, after some time, after some moment, you can say this OH bond is going to be mature and Br negative ion as a nucleophile, it leaves permanently to this molecule. And finally, we have made this alcohol that is, in this case, it is said to be, this one is said to be ethanol, specific name of this compound that is in this reaction. It may be any alcohol, but at the moment it is ethanol. Got it? Okay. Once again, I am going to repeat the procedure with another example. For example, I'm having this time CH3Cl goes to, and I'm supposed to react it with OH negative ion. That this OH negative ion is basically taken from sodium hydroxide aqueous. So what is the procedure? Yes.
So सीधा CH3OH बन जाएगा ना.
Yes. But
जो process है सर CH3Cl में OH attach होगा negative ion बन जाएगा.
good.
वो transition state कहेंगे will be very short lived.
Yes.
The अगला step वो OH वो Cl detach होगा will become a negative ion, so it will be Cl negative plus methanol.
Yes. Exactly. Plus Cl negative ion. So if you want to write it in a 3D formula, here is a carbon, and let's suppose one hydrogen. It is Cl over here, dotted line hydrogen, and this is the dark wedge hydrogen. This is the 3D structure of this CH3Cl. Right. So now the next step is, what is the next step? Write lone pair over here. You can say that mark partial negative, mark partial positive, and then you can attack from OH negative on this carbon atom. At the same time, this CCl bond is broken. Here is a transition state. I will mark square bracket over here and carbon, hydrogen. This time I'm going to show it with a dotted line. It was already by the dotted line, but this time I'm making it and changing it into the solid line, and that is a dark wedge of hydrogen. And this OH group is again shown by the dotted line and negative charge over here. Finally, we are going to make this one molecule, and this will be written as OH group over here. And let's suppose I'm going to write hydrogen and this one edge of hydrogen. Let me change it once again. The more appropriate way is to write this molecule like, I'm going to change as one, let's see, I'm going to change its representation. I'm already placing this Cl at this one, I'm in dotted line, and I'm placing this hydrogen at normal line, and this time you will make these two, you will draw these two, both dotted line. And finally, now in this case, whenever you are going to write this molecule, Now you will write it, I mean, this new incoming, I'm sorry, incoming OH group is lying over here, as I told you. So you can rearrange this molecule like that. Hydrogen and dotted line hydrogen, and you will make write it on the dark wedge of this one. So this is said to be inversion. The new geometry that has been made is said to be are known as inverted geometry and so on. However, this is a simple mechanism and there is no need to write inversion or retention, and this is the finally general main final product of SN2 mechanism. So in this case, nucleophile was or is OH negative ion. Reaction is heated under reflux, usually, mostly. Halogene do not mix water, so ethanol is used as a solvent sometime in both haloalkane and sodium potassium hydroxide and so on. So basically, whenever you are going to use, whenever you are going to mix two organic compound, it may not be miscible to each other. They are not going to mix, they are not going to solubilize each other. At that time, you will have to use any solvent. But at the moment, we are using aqueous solvent. We are not using ethanol. Ethanol can also be used. Yes, it is true. That is in elimination. But you will have to use any solvent. You will have to choose any solvent, either organic solvent or aqueous mean water, solvent, and so on. The last and important thing is this one. Whenever you are going to write the rate equation for this mechanism, then two species are the part of this rate equation. It means that what the rate equation tells us, it tells us which type of species can change the rate of reaction if you are going to change their concentration. So if I am going to change the concentration of OH negative ion, speed will be changed, rate will be changed. If I am going to change the concentration of bromoethane, yes, or chloromethane, yes, rate will be changed. So this in this mechanism, the concentration, quantity, amount, the concentration of the both reactant, they do matter to change the speed of the chemical reaction, and that is why it is said to be SN2 mechanism. Yes,
सर ये रेट इक्वेशन कब आती है?
ये जनरली A2 में है, लेकिन एक स्पेसिफिक आपको गिवन होगी, आपने बनानी नहीं है।
स्पेसिफिक क्या मतलब सर?
ये बनाने के लिए आपको या उस रिएक्शन के लिए आपसे A2 में पूछी जाएगी।
अच्छा ठीक।
अगर आपको गिवन हो ऑलरेडी तो आपको ये मालूम हो जाना चाहिए कि इसमें, यानी सिंपल आपको ये पता होना चाहिए, यू जस्ट नो either one species present in the rate equation or two species are present in the rate equation. ये जो 1 और 2 लिखा होता है, हाँ, तो ये जहाँ 2 लिखा होता है मीन इन दिस केस 2 species can change the speed of reaction. रेट इक्वेशन ये बताती है कौन कौन से रिएक्टेंट्स स्पीड को चेंज कर सकते हैं, और अगर यहाँ पर 1 लिखा हुआ है तो दैट इज गोइंग टू चेंज द ओनली वन स्पीशीज इज गोइंग टू चेंज द स्पीड ऑफ रिएक्शन. आई मीन जस्ट ऑर्गेनिक कंपाउंड्स concentration can alter the speed of reaction. If you are changing the concentration of OH negative ion, I mean nucleophile, there will be no change in speed if mechanism is SN1. In SN1 mechanism, generally speaking, there will be no participation of concentration of OH negative ion और न्यूक्लियोफाइल. आप न्यूक्लियोफाइल बहुत ज़्यादा ऐड कर देंगे तभी स्पीड नहीं बढ़ेगी. लेकिन if the reactant is following this SN2 mechanism, then if you are going to add more nucleophile, more NaOH, then definitely speed will be more, speed will be changed, and so on. That is all about this mechanism. That is generally the rate of hydrolysis whenever you are going to make hydrolysis. This is the same reaction, but this time I'm not going to talk about the mechanism. I'm going to tell you the another perspective, the general speed of hydrolysis. So hydrolysis depends on the two things. Number one, the nature of halogen, and next thing is the nature of secondary, primary, or tertiary haloalkane. So if Cl, if they're iodine, the basic uh, thing is their bond length. Ci bond is more easier, there is more ease, are the more speedy than CBr bond. It is more easier to break than CCl. It is more easier to break than CF. So basically, the basic the
Plus CF is hardest to break.
yes, the basic factor is this bond energy or bond length. This is the lengthiest bond, and its bond energy is weaker. It is easily broken as compared to CBr, as compared to CCl, as compared to CF. So CF is the shortest bond, is a stronger bond, and so on. The next thing is if you're having the tertiary haloalkane uh, are secondary or primary, then the more easier is the tertiary haloalkane. If you are having all, let's suppose tertiary haloalkane, this is a tertiary haloalkane, and this carbon is attached with iodine, and I'm going to compare it with this secondary haloalkane. Again, it is having the same nature of halogen, iodine. So which one is going to be more easier? Then obviously now the bond energy is same in both cases, and this tertiary haloalkane is going to be more easier.
अच्छा मुझे लगा जी जी सर.
Tertiary is more easier because whenever it's going to have the positive charge, there are three groups over here to compensate its loss of electron. But in this case, there are only two groups, and they both are trying to compensate the loss of its electron, its impact of positive charge by positive inductive effect. However, you can practically, if you want to check this, if you want to monitor this whole system, then you will add AgNO3 into this one. I mean, if you're going to do hydrolysis, then after some time you will add AgNO3, and then you will check either AgI is going to be formed, and I mean how long it takes to be formed or how long they are going to be formed. So this formation of AgI will let you know the reaction is happening and how easier it is happening, how rapidly it's going on or not. This AgNO3 is an inorganic compound. It is just added to make, to visualize, to identify the species that is being formed. So in this case, especially yellow precipitates are formed. As you know, AgI is a yellow in color, and its quantity, its intensity will let you know how rapid the reaction is going to happen, and so on.